if we assume or start with this concept that so the ground, my desk, and the launcher launching at 0 degrees, and it had to fall a distance of, we said 1.066. By the way, so did you measure to the center of the opening? I think you should measure to the bottom of the opening. The center of the ball doesn't hit the ground, the bottom of the ball hits the ground. It's only a ½ centimeters different, but every ½ centimeter makes a difference. I'd measure from the bottom of the opening. All right, so we can figure out how long it was in the air. This is just the vertical side. This is me taking a look at the delta y being negative 1.066, the acceleration being negative 9.8 meters per second squared, and the initial y velocity is 0, so I want the time. At this point, knowing that that's 0, I'm going to use my shortcut. Square root of 2h over g. Yep. So, this will be the square root of 2 times 1.066 divided by 9.8. And you guys got a time of what you said, 0.47? Is that right? Give or take a little bit? I wouldn't give or take anything. I would write down all of those decimal places. I would, or leave them in your calculator for the next calculation, which is to figure out how to use the range to tell you what the velocity was. We know the time is 0.47 seconds. You measured the range to be 2.22 meters. Since range equals Vx times t, the horizontal velocity should have been 2.22 divided by 0.47. 4 point what? 4.7 something something? I'd keep a lot of something somethings there if I were you. Now, here's where it becomes important to realize that this right here is not the horizontal velocity of every single one. This is the velocity of the launcher. It is V0. Ultimately, what we really have is 4.7 meters per second equals V0 cosine 0 degrees. That's what we really found, because the angle was 0 degrees. So, this is the only thing we can really carry over. This and the height. Because in the next part, got the ground, got my desk. But now we're launching at an angle of 30 degrees. 4.7 meters per second. And the ball still has to fall to the ground, which is 1.066 meters below. Let's set that up. Vertical, horizontal. The vertical is going to be delta y equals 1.066. Vy initial is now 4.7 sine 30 degrees. The acceleration is still 9.8 meters per second squared, and we want the time. Let's make upwards positive and to the right positive. That'll make this negative and that negative. There's only one way through this. Delta y equals 1/2 at squared plus vy initial times t. So, negative 1.066 equals 1/2 times negative 9.8 t squared plus 4.7 sine 30 times t. you have no choice but the quadratic formula of that sucker. That's all you can do. And you could plot it. Some of you know how to do that. And it's actually probably faster. But if you don't know what you're doing there, then you better be careful. Now, I don't know what you get for t here, but I bet it's more than 0.4 something seconds. I'm betting it's around, I don't know, 0.7 or 0.8 seconds. What is it? 0.77. There's another time that you're going to get, but it's negative. Do I need to worry about it? Nah. So I'm just going to ignore it. Horizontal, range, Vx, and t. We use this to find out that t was 0.77 seconds. Vx is going to be 4.7 cosine 30 degrees. The range, 4.7 cosine 30 times 0.77, which apparently is somewhere around 3.17 meters. Like I said, you're unlikely to hit the paper if you make a calculation mistake. And unless you do something really crazy, you know, the calculation mistakes you can probably mitigate if you're careful. Measuring's important though. It'll make the difference in an A and a D. That in this problem, number 5, that the arrow comes to rest at 31 meters and then falls back down. That this was the maximum height attained by the arrow, which suggests that delta y is 29.55 meters because it went from 1.45 meters to 31 meters. We all okay with that? And although we don't know how fast the arrow was launched, we know that at that height, the final velocity was 0. And the entire time, gravity is pulling downwards on the arrow at 9.8 meters per second squared. If we assume up is positive, then that makes gravity negative. I want to figure out how fast this bow launches arrows. So I'm thinking Vy squared minus Vy initial squared equals 2a delta y. So 0 minus my unknown launch velocity squared equals 2 times negative 9.8 times 29.55. So figure out Vy initial. It's probably the square root of 2 times 9.8 times 29.55, which, if memory serves, is somewhere around 24 meters per second. I'd keep some decimal places. Now, can I go to another page, or are you still writing down? I can move? Fantastic. Because the next part of the problem, I'm not going to say is deceptive, because that's the wrong word, but it definitely is carefully worded. We launch from 1.45 meters at some angle. They want to put a target 1.45 meters above the ground. I think they're trying to force delta y to be 0 for this projectile. That's how I see this problem. With a vertical side and a horizontal side, we don't know what the range is. We're asked to find the range. We don't know Vx, but it's probably 24 cosine the launch angle. And isn't the launch angle 30 degrees? Today might be the day I lash out irrationally. I mean, just get to where you're going already and scrape some paint. When I post this video tonight and you hear the beeping, make sure you understand there is no beeping, because it's going to be in the recordings now too, forever emblazoned on YouTube, because YouTube never forgets. So when they say there's no beeping, there's beeping. I clearly hear beeping. I'm afraid, though, that I'm going to start hearing beeping when there is no beeping and won't be able to tell the difference. Do I have to keep going? I'm happy to, but I have everything I need on the left side to figure out what the time is. And I can plug that in for time on the right. Are we good? or keep going. It's up to you. I can probably help you set up another question, or I can finish this one out and tell you what the range is. All right, you worked out for. I like this question because it makes you think a little bit too. 10 degrees, unknown launch velocity. Apparently, there's 69.5 meters from one side of the canyon to the other. I have every reason to believe that he lands at the same height that he was launched at. So this sounds like another problem where, ooh, that's pretty rough. Vertical, horizontal, where delta y is going to be equal to 0. Vy initial is going to be v naught sine 10 degrees. Acceleration is going to be gravity, 9.8 meters per second squared. I got to find the time. Doesn't appear like I have enough information on the left to find the time because I don't know v naught. So let's check the horizontal. The horizontal, the range is 69.5 meters, and the horizontal velocity is v naught cosine 10 degrees. Again, I don't have enough information to find the time because I don't know v naught. This shouldn't stop me. Look, the procedure is solve for the time on one side, plug it into the other. I have time in terms of v naught in two places. So I'm going to take this and plug it in for time right here. I'm going to use delta y equals 1/2 a t squared plus v y initial times t. This will be 0 equals 1/2 times negative 9.8. I didn't make it negative here, but I'm going to make upwards positive. Times t squared, which is 69.5 over v naught cosine 10 squared plus v naught sine 10 times 69.5 over v naught cosine 10. Now, that looks pretty cumbersome. Mind you, I'm assuming I can put this way up at the top so that you guys can see it easier. Looks pretty cumbersome, doesn't it? But it's just one equation and one unknown. The unknown is v naught. And in fact, I can cancel it out right there because I have one in the numerator and one in the denominator. And I got a 0 going on right here. So I'm not so sure that this is all that tough now. Yeah, there's squareds in there and there's numbers to multiply, and I feel really bad for you and all, but not so much. I could keep going if you'd like to see it continued, because some people do have difficulty with this level of arithmetic. Would you like me to continue? Okay. First thing I do is 1/2 times 9.8. And actually, I'm going to take this entire term and move it to the other side of the equal sign. Because I have a negative here, that'll make that negative positive. When I do that, I'm going to get 4.9 times 69.5 squared divided by v naught squared times cosine 10 squared. I just distributed the squared. And that will equal 69.5 times sine 10 over cosine 10. Now I'm doing this to illustrate a purpose, but you could just type sine 10 into your calculator and get a number, and then type cosine 10 into your calculator and get a number. I want to illustrate that you have sine over cosine here. That's not accidental, it's tangent. If you don't remember that from last year, or whenever you learned it, or if you never learned it, sine over cosine is tangent. Do you all know that? If not, write it down, because it's true. So this is actually 4.9 times 69.5 squared over v naught squared times cosine 10 squared. And that equals 69.5 times tangent of 10. Now, let's face it, cosines and tangents, they can all be plugged into your calculator. What some of you need is what to do here. And I'll be honest, cross multiply. That's what to do here. Put this over 1 and cross multiply. That'll get v by itself eventually. I'm running out of space here. Is this good enough? Or keep going? All right, I'm going to stop here. I'd put this in your notes someplace. I want to consider the type 2 problem. The one you just saw. But I want to continue it with just placeholders. I don't want to put any numbers in it at all. I'm going to write the range as R. And I'm going to write Vx as V naught cosine theta. That means T is R divided by V naught cosine theta. The other side, delta Y is 0. This is special. We're doing a type 2 problem. Delta Y is 0. That means Vy initial has got to be V naught sine theta. Acceleration is going to be G, the acceleration of gravity. I'm just going to put a G in there as a placeholder. Told you I'm doing the whole thing with placeholders. And I'm going to make upwards positive, so my acceleration has to be downwards. It's negative. If I were to use R divided by V naught cosine theta, I could come up with a relationship for a type 2 problem that tells me the range without having to do substitution. Meaning I can come up with one relationship. This is called the range equation, and I'd like you to see it done. I'm going to move this up a little bit because I'm assuming you guys have been keeping up with me. And I'm going to write delta y equals 1/2 at squared plus vy initial times t, which for this translates into 0 equals 1/2 times negative g times r over v naught cosine theta squared plus v naught sine theta times r over v naught cosine theta. Now, some of you aren't going to be able to follow this, and I forgive you. It's okay. But many of you can follow this, and I really want to speak to you guys for just a minute. First, I can move this entire term to the other side. I'd like to do that. And when I do, I get negative g r squared over 2 v naught squared cosine squared theta. This has to equal v naught sine theta times r over v naught cosine theta. Yep. What negative g? I don't see a negative g. Must be. I'm hearing things, you're seeing things. Now, if you didn't follow all that, it's okay. I'm just not talking to you. Pay attention to the result. Because I can cancel out an r with this r. I can cancel out one of the cosines with that cosine. It's not 0 because I'm not launching at 90 degrees. And I could cross multiply on that side after I get rid of these two v naughts. When I do that, I get g times r equals 2 v naught squared cosine theta times sine theta. And yes, that math works. In fact, I can go one more step and write this as 2 sine theta cosine theta all times v naught squared over g. I know some of you are trying to squint to see way down there. How about I do that for you? Does that help? Now, I would love to stop here, and I could. This has got some interesting things in it. It looks like if I have the launch angle, the launch velocity, and g, I can tell you where it lands without ever solving for the time. Because you can, we eliminated time. But how many of you remember that there are trig identities out there? You should look this up. It's called the double angle formula, and it's pretty magical here. Make this substitution, please. It's worth knowing. We'll talk about the implications of this tomorrow and finish going over the homework.